Okay, magnets. How do they work? Well, that's a pretty complicated question, but we're going to start off with something a little simpler. We're going to start off with the things that you probably already know. So, first off, magnets have a north and a south pole. Technically, this is a north-seeking pole and a south-seeking pole, because the north pole of a compass, which is just a tiny magnet, points toward the north pole of the Earth. But opposite poles attract and like poles repel. So the north pole of the Earth must be a south pole, right? Magnetic north is a magnetic south pole. So it's like we have a magnet in the Earth that is upside down. So something else you should know, of course, is that the north pole that is the axis of the Earth spinning that north pole, geographic north, is not the same thing as magnetic north. Geographic south is not the same thing as magnetic south. Geographic north and south stay very close to constant. The Earth wobbles a little, we call it precession as it spins, but they're pretty close to constant. Whereas the magnetic north and south pole wander around like crazy. They can end up hundreds of miles away from where they were a century ago, and they actually are wandering faster and more chaotically lately than they have been in recent decades. Something else you should know is that some materials can be magnetized and some cannot. You can magnetize iron. You can magnetize some types of stainless steel, but not others. You can't magnetize copper at all. There's a great video put out by Minute Physics and Derek from Veritasium on the nature of magnets and magnetism, getting down even to the quantum mechanical level. It's a great watch, and I'll put it here and in the description down below. You should check it out. Meantime, check out this little bit about paper clips. I've got a paper clip, I've got another paper clip, I attach the one paper clip to the other by touching it, and I let go, and they are not magnetic. They do not stick. Well, I have a magnet. It's definitely magnetic, right? It sticks, paper clips stick to it no problem at all, right? Okay, now if I take that non-magnetic paper clip and I attach it again, suddenly it sticks. That's pretty cool, huh? Check this out. It still sticks. If I pull it off, I might even be able to get it to re-stick. Oh yeah, look at that. Cool, huh? So what just happened here? This paper clip is now magnetic. They weren't a moment ago, and they are now. They're not extremely magnetic, but they're definitely magnetic. If I want to demagnetize them, I could treat them with a little bit of subtlety. You ready? Now, let's try again. No longer magnetic. What's going on here? So you see what I did there? I took something that was not a magnet and I turned it into a magnet by exposing it to a magnetic field. I then turned it not into a magnet anymore by beating on it with a hammer. I could have instead hit it with a torch, but they frown on me bringing those to school, so I did not. But fire or jarring with a hammer have what in common? They cause random motion. So what is it about organization and disorder that causes something to be magnetic or not? Well, if you watch that Minute Physics Veritasium video, you already know the answer, but here it is again. In anything that can be magnetic, in anything that's ferromagnetic, there are tiny little clusters of atoms that we call domains, where all of the atoms are each tiny little magnets, and they're all lined up in the same direction. If you have a bunch of domains that are all scattered and pointing in a bunch of different directions, that magnetism all cancels each other out. Now this picture is it's way too big. These are microscopic structures. But you have millions of these little microscopic domains, and if they're all pointing in different directions, then the material overall is not magnetic. But if you can coax them to turn into the same direction, where the ones that are pointing the right way get bigger, and the domains that are pointing the wrong way get a little smaller, and they all face the same way, then you can turn it into a magnet. So what did banging on it with a hammer do, or hitting it with a torch do? It disrupted those domains that had been organized by that previous strong magnet. Materials that are easy to magnetize or demagnetize are called soft magnetic materials, and materials that are very difficult to magnetize but they're hard to demagnetize if already magnetic, those are called hard magnetic materials. It has nothing to do with whether or not the material itself is soft or hard. Iron is awfully hard, but it is a soft magnetic material. One more point about magnets that you should know, and that is that magnets are dipoles. They have a north and a south pole. If you cut a magnet in half, you end up with two magnets that each have a north and south pole. You cut those in half, you end up with four magnets that each have a north and south pole. It's not separable. Unlike electric charge, where you could have a positive charge by itself or a negative charge by itself, you cannot have a magnet that is just north or a magnet that is just south. All magnets are dipoles with both a north and a south pole. So there you go. Those are the things that you should already know about magnets. In our next video, we're going to talk about the magnetic field in a little bit of detail.